strategies. For example, you failed in this case.
Yeah.
Is there any obvious? I find probably for the linear algorithm, so the earlier one was ON. So probably improve upon that.
No, but we will see even in ON we will be able to improve in this. The constants we will improve, right? So we are going to see progressively several solutions which are improving by 15% and 25% and like that. We will be able to see some interesting twists to this. I will not give all the detail, but some detail I will discuss here, which is relevant to get the grasp of how some improvement can be done using a strategy. Right. This is more a case study for explaining divide and conquer strategy. Right. And we will use it to show merge sort and other things improving significantly, quick sort improving significantly.
The bottom line was we need to look into every element.
Yes.
First algorithm that we did exactly that.
Right, right.
Also that finding the minimal distance between the points. That problem can also be solved using this divide and conquer.
Yeah.
There's also convex regions and interconvex regions.
Yes. Except that while combining the solution you have to be extremely careful. If you are not careful, the problem could become very messy.
Because the adjacent points may be in two different convex
regions. Yes.
They can be the smallest ones.
Yes. And locating them is not easy. So it's a lot of work. Careful, we have to be very careful about it. But yes, it is doable that way, and you have an n log square n solution, n log cube n solution, and n log n solution. Each, one more sophisticated than the other. The n log n solution is very complex.
Professor, one more thing in that gate problem, we are taking in 2 powers. If you are increasing that power, for example, 2 power k is greater than 4 like things, we can take 4 and multiples of 4. That time we can get still less than that 7n minus.
Yeah.
So as much as possible, for example, in the next iteration we can go for 8.
No, going by, see, the actual solution is like this. If n is of the form 2 power k, going by 2 power k will give you a good solution. But if n is of the form 3 power k, then going in factors of 3 will be helpful. When n equal to 3 power k, if you gallop like this, it will cause overhead. Right? So if you have a knowledge of n, that can be used a little bit. But if you don't know anything about n, then none of these things will work. You can as well work with one galloping strategy. And every galloping strategy will be as good or as bad as any other galloping strategy when n is not known. But if n is known to be 3 power k, galloping by factor of 3 is better than galloping by a factor of 2. That will be revealed by your analysis.
Or else can you go by steps of prime numbers?
You don't know the next prime number. That's the problem. Alright. We don't have the full list. And computing the next prime number is difficult. Whereas here the strategy is simple. Any other question or comments that you have?
Just a comment on the last one that you said. If you don't know the pattern of n, it's better to use 2 power k, galloping using 2 power k.
Yeah.
That would save to a certain extent, because even if we miss out, the miss out will be by just one side only. Either if it's not a power of 2, it's just something between the next 2 to the power of k and 2 to the power of k plus 1. So your miss out factor will be lesser when you gallop by 2 to the power of k.
That's right.
Instead of doing on 3 to the power of k.
You can argue counter also. So typically you miss actually only once.
Yes. Then we
So you gallop fast to reach that miss point.
Yes.
That's the point, yeah. But the analysis will reveal that well, we have here a code tuning also can be done. Implementing the jump by power of 2 is easier than power of 3. So, but that's an issue related to code tuning, not on algorithms. That is typically known as replace a complex function by a simpler function. Complex computation to be replaced by equivalent simpler computation. Yes. This lower integral part, floor and other things, these are all messy to compute. In fact, that's the reason why binary search, instead of doing it with this plus this divided by 2, floor 2 operation, take the nearest power of 2, you can split anywhere, it's going to be smaller or larger. So, first you take the most significant bit portion of it and then you split it across, and then onwards it is all going to be factor of 2, which is easy to split and divide. So, you can find the point at which the index which you should choose for comparison can be done in a very simple manner. Alright. So, binary search can be significantly improved, made faster by that code tuning technique. But again, that's only code tuning. The strategy is same. Choose a pivot to compare and proceed for the next stage either to the left or to the right, ignoring the right or the left.
I have just one question.
Yes?
We have seen all these patterns, everything. But in your real life, where have you seen this implementation in industrial production?
Oh, everywhere, everywhere. Any problem that you see here.
No, not with respect to graphics, because graphics works on all pixels and data. Apart from that, like when you go for computing in normal scenario.
See, in most of the database application, for instance, okay, the queries, and then you have to do a lot of searching, and then you have to consolidate the data, the join, project operation, all of them involves plenty of array manipulation, merging and computation with them, sorting. Everywhere you will see that these kind of things are used, and then an efficiency improvement here would correspondingly contribute for the efficiency there. I am going to tell you some real life instance. In fact, I would recommend that I have brought that book. I will bring and show to you tomorrow. These are all the stories by John Lewis Bentley. He was an algorithm consultant at Bell Labs. He has done a lot of real life practical situation where he has applied this wisdom and then speeded up. For instance, in Bell Labs they have written a driver for printer plotter, and then they wanted to, when they implemented that, they found that it is taking enormous amount of time. That is because they wanted to minimize the pen distance movement, starting from one position, going to various places and coming back. And they happened to implement the Hamiltonian path problem in such a naive way, which is an NP-complete problem. And then the moment he saw the solution for that, he realized that they have really got a very messy solution there. He replaced it with something which has reduced it drastically to something less than 2 seconds. So identifying the hotspot, seeing what is inefficient there and how to replace it with a better solution, all these things are the part of drive for improving the efficiency. So like this, there are several success stories in his career. He published that as a series of articles in Communications of ACM. Between 78 and 81, if you see CACM, then you will see number of articles. Every month he will write an article on how in his profession he has brought about certain significant speed up in a particular case study. He will give the complete description of the problem and his ideas on that and how it improved upon that. He will give industry grade case studies. None of them are fictitious, they are all real life case studies. That one was published as a book now. It's called Writing Efficient Program and Programming Pearls. And I have brought those books here, and you can see that I use them as a supplementary material for my course, because people have to go through the same process and then see how those efficiencies could be done in their code tuning as well as in their efficient implementations. So it's extensively used. It is really a big fund of knowledge on Unfortunately, little later he stopped writing that article, but I know that he is very active. He's a very smart person who gives consultancy services to whenever somebody is stuck with a product which is performing very poorly, it will be given to him. He will profile various parts of execution, identify that part of the segment of the code which is taking maximum amount of time, isolate the inefficiency, replace that module, and then he will bring in overall efficiency and so on, and he narrates his real life experience in those articles. All of them will treat the topics that one would typically see in the data structures and algorithm course in undergraduate computer program course. So when we use this as a supplementary material, people will immediately connect what they are learning in the class to some industry grade practical applications. That is not only of interest and use to the classes. We could now see that these ideas are all very useful there, so we can look forward to this kind of situation when we do the professional practice. Right? When we encounter some such problem, whatever he has done, we can also imitate and then try and then see whether we could gain some, bring in some efficiency in our context. And that's a constant struggle. It will be on forever. But all real life experiences are there in that, summarized in that book. It's a very well written book, an extremely well written book. I would recommend that be available, several copies in the library, and every one of you, it's very delightfully written. Each is a 4-page or 5-page article. You can almost read like a novel in your bedside, but each one will give you such a deep insight into the efficiency methods and application of all these principles and strategies. Really good book. I would strongly recommend any article by Bentley. Anything by Bentley you can read.
Most supplement book is called Some More Program.
Yeah, that's right. All of them are classic writing. Each one of them is, each article is a beautiful article. See, every one of us will do something or other, but we are not recording many of those things. I'm sure if a person has got programming experience of 10 years, during his long experience, surely he would have found something in the first attempt he would have implemented in a naive way, and it wouldn't have really been satisfactory. He himself would have improved upon it, and there he would have come up with some innovative ways of handling it and so on. But then it will all be buried in that ton load of code, some of them under intellectual property rights, some of them could vanish, it may not surface at all later on. Many things may happen. Lot of interesting ideas are generated, but not many of them are even recorded. Bentley's attempt is the first attempt of its kind, that is why this is a celebrated book. Any practitioner must refer this book for such insightful writing and comments. Really a delightful book to read and write. Okay, so I stop at this point. We will see you tomorrow. Okay, so shall we start? Okay, good. So welcome to the session again. We are now looking at paradigms, patterns of wisdom for solving problems. Problem solving is something that the humans encounter all over. We encounter difficulties, and then we come up with a clever way of overcoming the difficulty, and we get ideas to solve it. The algorithm design is no different from that. Some of them are stated in nice stories. The famous Panchatantra story, which tells you that a bunch of twigs, when a brute force is applied, one could not break, whereas one takes one twig after another, and when you could break it, everything can be broken. That wisdom and incremental design is no different, except that it is stated in algorithms, complexity and stuffs like that. But basically it is one way of solving the problem. If everything there is to be broken, do little by little, and you are eventually accounting for all the twigs that are around. So in the same way, the divide and conquer also has got, it's actually a war paradigm. Okay. It's recorded in the history how Babur has conquered a mighty force in India, and in the recent past how Napoleon has managed to split the crowd, split the Allies forces and then won each part separately. So divide and conquer is a very famous war paradigm, and that's what we have embarked on to see how it is. So what is complementing for so design paradigms? First, incremental. We are going to see a close relative of this, actually the complementary view taken for this, that is decremental design. And we are going to compare and contrast this with divide and conquer. So let us look at the decremental design now and come back to the contrasting part of this. In decremental design, we relate a problem to something smaller in instance. Solution of a problem will be related to the solution of a smaller instance. This immediately you know that it is nothing but recursion. Okay? So the decremental design is nothing but recursion, but then we are going to look at various flavors in which the recursion can occur and can become effective problem solving tool. In the simplest form of recursion, I will have only one recursive call made. Okay? The God given example is f of n equal to n into f of n minus 1 and f of 1 equal to 1. This defines the function factorial n, f of n equal to n factorial. So if you want to compute this value based on this recursive method, you can write a recursive program. In fact, most of the recursive programs will be illustrated and taught using the direct implementation of this recursive formulation. Okay? There are many situations, at least in situations like this, the recursive formulation tells you how to extend a solution for a smaller instance to a larger instance. In other words, if I know f of n minus 1, I know how to get f of n, I have to multiply it by n. So from this, I can get an equivalent incremental design which is going bottom up. If this is a top down, just the other way around will tell you a way to incrementally arrive at the answer. So start from 1, multiply it by 2, multiply it by 3 and so on, and you can multiply up to n, and that is incremental. Whereas this is a decremental, the equivalent other way view is incremental. This is decreasing by a fixed quantity, therefore it is possible for you to see the equivalent incremental design in an easy way. Okay? You know how to extend 1 to 2, you know how to extend 2 to 3, and you know how to extend from 3 to 4. You have to do some computation that is simple and that is indicated by this recursive formula. Okay? So let us look at another example. In this, if you consider a power n equal to a power n by 2 into a power n by 2 if n is even, that is equal to a into a power n minus 1 by 2 into a power n minus 1 by 2 if n is odd and n is greater than or equal to 3. If n is equal to 1, it is a power 1, which is so equal to a if n equal to 1. So a power n equal to, now I am now relating something to something smaller, and this is called a recursive definition, okay, or recursive formulation. It looks artificial, right, saying a power n in terms of this, but I am now relating it to something. You can write like this also, a power n equal to a power n minus 1 into a. There is no problem. This is also, it is much like this. But when I write like this, what happens? I am able to now relate something which is substantially smaller, and now I can have an equivalent iterative program which is built bottom up, and that is what we have seen in the incremental design. Okay? So, what is the incremental way of looking at it? Multiplying 1 with 2 with 3 with 4 in a for loop, you can write like this. So, you can have a recursive function based program, you can have a for loop based program, and here also you can have a recursive program terminating at this condition, or you can have a for loop based program which we saw yesterday. Okay? You start from that and you look into the binary representation of it and square and add. So, if it is even, that is if the next bit is 0, that means it is an even number you have considered at that point. So, you are going to only square it. Otherwise, you are going to square and multiply, right? Because when n is odd, you take 1 away, that makes n minus 1 even. If n minus 1 is even, n minus 1 by 2, n minus 1 by 2 makes sense. Therefore, you can write like this. From this recursive formulation, when you try to go bottom up, you get an incremental design, and that incremental design, incremental solution takes only logarithmic number of steps. Okay? So, why are we doing this? There are two reasons why we have to look at certain things in this way. The two reasons are, one is recursive formulation is easy to make. Usually, if you try to decrement a little bit and see how that solution and this particular solution is related, is somewhat easier for you to look at. Hence, recursive formulation is easy to make. However, the practical situation, the efficiency demands that from this recursive formulation, do not go to recursive program. Do not immediately jump to a recursive program from the recursive formulation. There are two reasons. One is, when you make a recursive program, it will have lot of function calls, function call related overheads. Every function call has to maintain lot of references, and then it has to pass the parameters, store the values, whether it is call by value, call by reference, and then plenty of such bookkeeping related work you have to do. Every function call is going to cause enormous amount of delay. Okay, you have to store the reference, go to that point and then do computation, return that value, everything. So, other than what you are supposed to do to obtain the value, what all you have to do is multiply n numbers, and in that process look at the programming overhead, some parameter passing and calling and function returning certain values, using them to build something. So much of overhead we have built, and that would be the characteristic of recursive program. Whereas when you write for I equal to 1 to n, s equal to s star I, s equal to 1, s equal to s star I, you do precisely just whatever you are supposed to do. There is of course little bit of bookkeeping overhead, but that is minimal. Okay. Therefore, you may make the recursive formulation because easy to make, but it is always preferable to have an equivalent iterative program written. Okay. So, instead of writing a recursive code based on it, which will make a lot of function call, get that incremental one. Sometime it will be very difficult for you to arrive at that incremental solution. You may not know how to extend, you may not know the order in which it has to be done. In that case, you start from this, but this formulation itself may give you enough hint on how to extend. Okay, this tells you how to extend a solution from a smaller instance to a larger instance. So use that and then come up with a program, okay, which is based on it, but it is incremental in nature. So do not go to it. So the recommendation is attempt an equivalent incremental solution. This is iterative in nature. This is basically bottom up. Recursive formulation is top down. Okay. Why did I say attempt? The reason is there are certain problems whose recursive solution is easy to formulate, but its equivalent iterative program is either very impossible or either it's very complicated or even impossible for you to arrive at it. It may not even make sense. So I'll give two examples of that kind. The first one is finding the standard example, again explaining recursion, the Tower of Hanoi. In the Tower of Hanoi problem, you have 3 pegs and there are progressively smaller sized disks piled on one peg, and you are supposed to move them to other peg. You are allowed to move one disk at a time, but at no time you are permitted to keep a larger disk on a smaller disk. Well known problem. The recursive formulation is easy to make, but trying to obtain an equivalent iterative program is extremely complicated. Try that yourself to feel the difficulty. Okay. From this recursive formulation, you are able to get an equivalent iterative formulation easily. Again, from here you are able to do that. Try this one. It is decrementing by 1, but still attempting to write an iterative program equivalent to this in a bottom-up fashion is going to become extremely complex and tedious. In this case, from the recursive formulation, go directly to the recursive code. Okay? That is because it is very difficult for you to think of a bottom-up based solution. So you should try. That's the reason why I said attempt. If you are successful in this attempt, this will be much more efficient. Why? No function calls involved in it, straightforward computation, and overheads are minimal, and hence this will be much more efficient than this. So if you run the program for finding the factorial n, a recursive program, and this iterative program, obviously you will see significant improvement in this, basically because a lot of overheads are spared in this. So this is what we say as replace a computation module with an equivalent one that is getting the same job done in a simpler way. Okay? So there could be several ways of doing certain thing, and you have to get it done in the simplest way. This will fall under the code tuning category because the computation that you do here as well as here, the algorithm wise they are same. But what we are trying to do is, instead of this code, I am plugging in this code. Okay? My approach is same, but the computation, the labor involved is same, but bookkeeping mechanisms involved here is much more and bookkeeping here is much less, and that is bringing in certain level of efficiency. Okay? This you may or may not be able to achieve, so you have to attempt. And when you are successful, go ahead with this. You always have a much faster and more efficient, sleek, easy to understand code than mysterious recursive calls, functions and all kinds of things. So where possible, you do that. We will see some advanced examples of that as we go along. So Tower of Noi is one example. Another example which is also well known and most of you are familiar with is finding the GCD. Finding the GCD of two numbers, greatest common divisors of two numbers. So you have GCD of AB is denoted like this, equal to GCD of B A mod B. This is well known. In fact, this is what Euclid has, the first algorithm, the so-called algorithm that was designed by a human ever and presented, etc. It's a very celebrated, there's a lot of interesting history for this. You can take a look at many of the resources available in the web to get some historical and anecdotal background for this. Okay. So if we assume A is greater than B, if A equal to B, GCD is same. When they are not equal, one is larger, another is smaller. Right? So you put first here and this is smaller. First component is reduced to B, which is smaller, and A mod B. Mod B means it is a remainder. So remainder is going to be smaller than B. Maximum it could be B minus 1, but surely it is less than B. So the second component is also reduced, first component is also reduced. So starting from AB, you have something smaller. When you do it again, you will become something smaller. In this way, you keep doing it, it becomes a smaller and smaller. Okay. So you are relating something which is smaller, but here you see that it is by some exact quantity. There you do not know by what extent it is reduced. It all depends on the values of A and B. Okay. So it's not clear by what extent it is, and subsequently again when you use by what value and what extent it is going to reduce, you are unable to see. Okay. So there is a decrease that is taking place, but the quantum by which it is decreased is unknown. It depends on the input values. Here algorithmically the decrement is by 1. You relate something to which is smaller, but it is smaller by one value. It is smaller by a factor of 2. Exactly you know by what quantum it is smaller. That is the reason why you are able to build back by supplying that kind of a jump or that kind of an increment. You are able to build the equivalent one. Here it is very tricky, since you do not know by what quantity it would reduce. There is no way of finding by what quantity it should be incremented or extended. So this is another situation where you are not going to think of an equivalent iterative one which is doing bottom up or something like that. That doesn't make sense here because there is no way this would work. Okay. Also with respect to this GCD, the moment you hit the lowest point, you halt there. So there is no question of starting from a GCD finding these two number AB. That doesn't make sense at all in this case. Okay. So when you look at a particular problem, you see that how it can be formulated. Do you have a straightforward incremental solution possible? If there is an incremental solution possible, you see how it could be incremented. Can I increment in small values, or can I jump and gallop and then go to the answer? Explore these possibilities. But that does not give you any clue. Look at the decremental design. See whether a recursive formulation is possible. If a recursive formulation is possible, then you have the problem solved at one level, but you need not go to a recursive program. You see whether the recursive formulation you have done is leading to a nice incremental solution, a solution which you could not imagine. Starting from the blank, you might not know how to extend, but this recursive formulation might give you a clue as to how that incremental algorithm could have probably been designed. Okay? If that happens, you are now in a happy situation and go ahead with the equivalent iterative program and so on. But you are successful in recursive formulation, but you are unable to get a equivalent iterative one, then what you need to do is go ahead with the corresponding recursive code. So that should be taken as a last resort. That is because the overhead due to function calls and recursive program calls, bookkeeping maintenance is really enormous. Okay? So these are all certain points I would like to mention in related to incremental and decremental design. And as a programming challenge, you can ask the students to produce an iterative code for Tower of Hanoi problem. You see how people really struggle, right? And in order to have that fun, you first struggle yourself. You just see whether you are able to get one iterative program, okay? No recursive call. It should have only while loops and for loops and stuffs like that. See whether you are able to produce one such code for solving this problem. And then you will really understand the power of decremental design. Okay, there are situations in which this is the only way you can probably even think of a solution. The alternative ways could be extremely complex. It is possible. It's not that it is impossible, but it could be very complex. We are trying to trigger that intuition through toy example. This is an example only to give that kind of a feeling. There is no application for this Tower of Hanoi. Okay. This is not the purpose. The purpose is different. It has only pedagogic value. GCD of course has got application all over. Every cryptography algorithms and network security based primitives, we will extensively use finding the GCDs. All right. So let us come back to our recursion. In the decremental design that we have seen, I am relating a function or relating the instance solution to an instance to only one sub-instance. In other words, there is only one recursive call made in the formulation. However, in the problem that we have seen, like in divide and conquer, we are making two recursive calls, right? So a function can trigger two recursive calls, and that in turn can trigger two over here and two over there, and that way it is now expanding. So the number of recursive calls that are made could become extremely large. Okay? So we have to be a little careful in handling a recursive formulation in which multiple recursive calls are made. Okay? One way to understand the recursion is to view the so-called dependency graph. Suppose a function f of n is depending on n minus 1. You have to do this computation before you can go for this, and so on, and you have 1, and once this is there you can return this value, and this would return value, and this in turn would return the value, and this in turn returns a value to the calling environment. So if there is only one recursive call, you related to something smaller, and that gets related to something smaller, and so on. At the smallest instance you solve trivially, okay, and then return the values back, and that completes the chain, and so on. So function finally returns a value to the calling environment. So when there is only one recursive call made, the dependency graph is going to look like a chain. That is what I have done here. But if it is multiple recursive call, it is not going to look like a chain. In fact, it is going to look like a tree. Okay? So let us see T of n equal to T of lower integral part of n by 2 plus T of upper integral part of n by 2 plus 2, which we saw yesterday, and T of 1 equal to 0. This is the recurrence equation we have seen for the complexity, but look at the program itself, recursive code. The recursive code min max, right? Suppose I trigger min max 12. What it will do? It will call 6 and 6, because A1 to A6, A7 to A12. So this is of problem size 6, and that is of another problem of size 6, and this is going to trigger something like 3 and 3, and this will also trigger 2 recursive calls, and this 3 will be split into 2 and 1, and this will be split into 2 and 1. And this 2 will be split into, because the base for recursion is, recall the way in which the factorial function is, you can say, let us say fact n int or whatever, if n equal to 1 return 1 else. Yeah. So this is the base case, this is the recursive part, this is the recursive part, this is the base case. So until the base case, so this particular call can return the value 0 immediately, but this one has to be further fragmented, and this will be okay. So how would you find the minimum and maximum of two element according to the algorithm that we have written? If you want to find the minimum and maximum of two element, split the two element into two parts, one consisting of one element, another one consisting of another element. Find the minimum and maximum of this element, find the minimum and maximum of this element, combine them to get the minimum and maximum of the two elements. Okay? So let us say you have A1, A2. This will be split into A1 and A2 here. And how do you find the minimum and maximum of A1 and A2? Simply return A1 min 1 equal to A1, max 1 equal to A1. Here min 2 equal to A2, max 2 equal to A2. These two values are returned, and min 1 and min 2 is compared to find the overall minimum, and max 1 and max 2 is compared to find the overall maximum. Okay? So you make two further comparisons and you are going to output min and max. So the min and max is output after two comparisons, which is seen here. T of lower integral part of n by 2 is 0, T of upper integral part is 0 plus 2, therefore T of 2 equal to 2. And that is what is happening here. Okay? But You see here, you are making absolutely wasteful comparison, because min 1 is A1 and max 1 is A1 and min 2 is A2 and max 2 is A2. When you are trying to compare min 1, A1 and A2 is compared. Again, when you are trying to find max, A1 and A2 is compared. You are making a useless comparison here. So for two elements, at least there is a way to simplify it. When there are two elements, how do you find maximum and minimum? It is simple. Okay? If A1 is greater than A2, then max equal to A1, min equal to A2, else max equal to A2 and min equal to A1. So when there are two items, I can solve in one comparison rather than two comparisons. So now I am going to write my recursive program like this. Okay? So let us say min max A 1 dot dot n min max. If n equal to 1, what you should return? Min equal to A1, max equal to A1. Else, if n equal to 2, I plug in this code. If A1 is greater than A2, then do that. So, okay, plug in this code here. Else, I do the recursion. Split the array into two parts. Find the min max here, find the min max there. Therefore, you are going to combine it. Okay. So now how will the recursion tree for this look like? If you take the same 12, it will look like this. Take 12, you are going to split into 6 and 6, and then 6 will be split into 3 and 3, and this will also be split into 3 and 3, and this 3 will be split into 2 and 1, and this will be split into 2 and 1. But on behalf of 2 also you will return a value, on behalf of this also you return a value. Okay? In other words, all these kind of recursive calls can be avoided. Every kind of this recursive call can be avoided. You can see that the tree has got smaller number of function calls made. Okay, 2 and 1. So you understand the recursive program by unfolding the recursion and see the this is called dependency graph, how various subproblems are related to others and contribute for the building up of the solution to the given problem. I need A1 to A6 whose size is 6, A7 to A12 which is of size 6 to be solved, and only when I have those solution I will be able to compute my solution for A1 to A12 and so on. For 6 you need 3, 3, and this is how you have put this. Okay. So what we have done here is we have avoided lot of recursive calls and fragmentation by terminating at a slightly higher level in the recursion. And this is very important. This is extremely important. When you are implementing a recursive program, see if it is possible for you to terminate at a slightly higher level so that you avoid heavy fragmentation of the input into smaller problem. Every recursive program will break the problem into smaller instance, which in turn will be broken into smaller instance and so on. If it is a chain like this, there is only one way to come back. But if there are broken into too many fragments, like you see in the multiple recursive call based formulations, right, you will see plenty of fragmented problems. Okay. In fact, in the tree, you know, these are called leaves. So these are leaves 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There will be 12 leaves here. That is understandable because the base for recursion is 1. Okay, that is where the recursion terminates. So that is the only value at which it can return. So until you hit 1, right, you have to keep breaking it. In other words, you have to break it in such a way that you break them into pieces, each of size 1. And only at that point you will return the value, which means your tree must have n minus 1, it should have n leaves. Why? Each leaf corresponds to one problem size, problem of size 1. This is the base for recursion. So until the base, this recursive code will keep relating it to a smaller and smaller problem until the base case is hit. So here you are going to split until you get problems of size 1. The problem of size 1 will not be split further, that is returning a value. But for 2, you cannot return a value. According to our formulation which we saw yesterday, the 2 is also to be split and then it has to do all these things and so on. In other words, you will split the problems. The tree which is representing the split will have n leaves, each with value 1. You know that every binary tree with n nodes, n leaves will have n minus 1 internal nodes. Okay, let me write down that. If a binary tree has n leaves, then it will have n minus 1 internal nodes. This is standard well-known property of it. How is this property useful in getting an understanding of the working? In each internal node, what you do, you are doing a combining, because this returns a value and this returns a value, and you combine them and you get a solution. So each internal node is representing the scenario where the solutions are combined to get a cost, to get the solution for that instance. So now I can assign the weights as follows. I want to find the total complexity. So how much is done on behalf of each node? On behalf of this node, how many comparisons are done? 0. Because no comparison is done. When n equal to 1, no comparison is done. So this is 0, this is 0. But when this returns the value, 2 comparisons are done. And this is 0. But when this returns, 2 comparisons are done. Now 2, 0, 0, 0, 2. Now you could see the pattern, right? When these 2 return the value, you perform 2 more comparisons. You perform 2 more comparisons. And when this returns a value, perform 2 more comparison and you return the value. So there are n leaves, and in each leaf, what is the number of comparison done on behalf of those leaf nodes? 0. So the total number of comparison is n into 0 plus n minus 1 into 2, that is equal to 2n minus 2. This is what we have observed. So this recurrence equation has a solution T of n equal to 2 into n minus 1, that is equal to 2n minus 2, and that is understood now through the tree. Okay? Through the tree here, we understand that. I haven't told you the exact mathematical technique of solving this and arriving at this answer. So these kind of functions are called closed forms. A closed form formula is you substitute the value of n, you get directly the corresponding value. You want to know what is T of 100, you put here T of 100 is 200 minus 2, 198. That's it, you get in one shot. But if you do not know this closed form, if you know only this, you have to compute. Suppose this is the only information you have. You have to compute T of 100. T of 100 equal to T of 50 plus T. So you need to have T of 50. That will require 20. Lot of computation you will do, and finally you will find T of 100 to be 198. But that you will get after plenty of computation. So this is the same function. This is a recursive formulation. This is a closed form formula. Only when a function is in closed form, I can compare. Okay? So when I solve this recurrence equation, I get this. Now I have made a modification. Here is a improved program. Here I have gained some efficiency. So how did I gain efficiency? I told you, do not break them mindlessly until the last level. If possible, you return it at a slightly higher level. Here we have seen at one higher level, and that is giving us some very interesting improvement. Now let us see how the improvements are done. So here for 2 you make one comparison, right? You make one comparison and you are finding it. And whenever you see 1, it is 0. And if it is 2, it is 1 and it is 0. 1, 0. And this is 2 again. There is no doubt about it. So how many leaves are here? The number of leaves are 1, 2, 3, 4, 5, 6, 7, 8. There are 8 leaves, of which 4 of them are having a weight 1, 4 of them are weight 0. Okay? So if I am not relating it to n, in this case it is 4 into 1 plus there are 8 leaves, therefore there are 7 internal nodes. There are 7 internal nodes. So 7 into 2, this is 18. Whereas here it is 22. 2 into 12, 24 minus 2 is 22. You see a visible improvement even for a small instance. Okay? What you can show is, in general, it is theoretically possible to show, fully rigorous mathematically it is possible for you to show that when you improve like this, the saving will be about 15%. It will be much less than 2n by 2, 2n minus 2. Okay? In fact, you can show that the exact complexity of this scheme is 5n by 3 minus 2. It is 5n minus 3 by 2. Now, one more optimization is possible, and that optimization comes from the fact that if a binary tree has n leaves, then it has got n minus 1 internal nodes. Okay, let me not use n. If it has got k leaves, it has got k minus 1 leaves. If the leaves are 1 and 2, right, some of them are 1 and some of, if all of them are 1, so you start from n. If you n, if all leaves are 1, then it contributes to n leaves. If some of them are 2 and some of them are 1, it is something midway like this. If I want to reduce the number of leaves, why not I have maximum number of 2, right? Let us have as many 2 as possible. If I have as many 2 as possible, then you will have n by 2 leaves when n is even, and when n is odd, n minus 1 by 2 plus 1, n by 2 or n minus. Let us consider 12 itself. Suppose I split 12 like this. 12 I split as 6 and 6, but I want to have only even leaves. I don't want to have an odd leaf at all. So split 6 I am going to split as 2 and 4. And 4 I am going to split as 2 and 2. So now you see what are all the leaves. This is one leaf, 1, 2, 3, 4, 5, 6 leaves, each contributing for 2. So 12 is accounted by 6 leaves, right? So if the input problem size is n, how many leaves will be there? N by 2 leaves. If there are n by 2 leaves, what is the comparison on behalf of each leaf? On behalf of each leaf you are making only one comparison, so n by 2 into 1. And how many internal nodes will be there? The number of internal nodes will be n by 2 minus 1. On behalf of each internal node you are going to perform two comparisons. So what is the total number of comparison? N by 2 into 1 plus n by 2 minus 1 into 2, which is equal to 3n by 2 minus 2. 3n by 2 minus 2. So my original algorithm had complexity complexity 2n minus 2. A very direct go down to divide and conquer. This is incremental 2-pass algorithm had 2n minus 2. Then I had a divide and conquer which is also 2n minus 2, divide and conquer, but split up to size 1. Okay. Then I could get 5n by 3 minus 2, this is divide and conquer, which is up to 1 or 2. You can go down up to 1 or 2. And if you can maximize the 2, that is 3n by 2 minus 2, this also divide and conquer, if up to maximum number of 2's and probably a 1. For instance, if I am trying to split 13, 13 will be split like this. 13 will be split into 6 and 7. 6 will be split into 2 and 4. 4 will be split into 2 and 2. 7 will be split into 3 and 4. 3 will be split into 1 and 2. 4 will be split into 2 and 2. So you have 2, 2, 2, 2, 2, 2, 6 2's, 12 plus 1, 13. So a problem of size 13 is fragmented at the leaf level into 6 problems of size 2 and 1 problem of size 1. Okay. So how many leaves are here? There are 7 leaves. So there will be 6 internal nodes. Of the 7 leaves, one of them is contributing 0, the other 6 of them are going to contribute 1. Therefore, there is n minus 1 by 2 into 1 plus, right, n minus 1 by 2 plus this one. So how many internal nodes are there? The number of internal nodes are n minus 1 by 2. See, the number of leaves are n minus 1 by 2 plus 1. Therefore, number of internal nodes is n minus 1 by 2 into 2 Okay. So now